Now that I disconnect the other cable, you will realize that we start seeing request timeout. So while it is saying request timeout, this link here is warming up. So this red button will soon turn green, and then the data will start following this other link to the destination than the other one, because the other one is terminated. Let's have a brief discussion on that topic, spanning tree protocol, which is a topic many students find confusing. In this video, I will try my level best to make it simplified for you to easily understand it. Before going further, I would like to remind you that the two major functions of spanning tree protocol are to prevent broadcast storm, whereby packets sent into the network will keep on circulating to the point that the CPU can no longer contain it, and then the entire network will collapse. For example, if you use this computer here to send a request to this one here, switches normally they send the request to any of the connected devices. So let's say now without the spanning tree protocol, this switch now you send your packet to this switch, it will forward it. This is switch number 3. Number 3 will forward it to number 2, and it will forward it also to switch number 4 here. Then switch number 4 will forward it to all the switches connected to it. Then at some point you realize that the same data is being circulating over and over in the network to the point that everything will freeze. So that is where the spanning tree protocol come in, whereby it will block some ports to prevent that loop. For instance, if you look at the diagram here, you will see some red dots here. Anywhere you see this red dot, just know that that port is temporarily blocked to prevent the loop. So therefore, the data will be used in the other parts. But in the event that the main part had a problem, this port will automatically kick in and the data will continue flowing. And the second function of the spanning tree protocol is to create an alternate path, just like I said earlier. For instance, now this device, you want to send a request here. The data will then, instead of the data passing through here, you will realize that this port is blocked. So the data will come through this switch here from switch number 3 here, it will come to switch number 2. It cannot take this part also because here is blocked. So it will come to switch number 1, and then finally to switch number 4 down here. This is the part our data will be taking. But in the event that along this part, one cable had a problem or got disconnected, for instance, let's say this cable spoiled here, the data, instead of passing through here, it will then, this link here will kick in automatically. Although I will do the practice, you see it. I just want to explain it for now. This link red here will turn green, then the data will start passing through here, coming to number 4. And the same thing applies to any other one. Before starting our configurations, it is important that we have our root bridge.
The root bridge acts as the leader and reference point to all other switches,
because all other switches will be referring themselves to that particular switch. I would like to use this switch number 1 here as our root bridge. That one I will have to configure it because by default, the STP will select one switch among all the switches that has the lowest.
Since the default root ID number of all switches is the same, then the switch with the lowest MAC address will emerge as the root bridge of your network. That is by default, but the problem with that is a weaker switch might appear to be your root bridge. But if you are to configure it yourself, you can choose the most advanced switch. That is why it's important to do the configuration by yourself.
So in this case, let's come to the switch number 1. Let's configure it to become our root bridge. I might sometimes call it our main switch so we can easily understand it. By default, every switch has the root ID of 32769. That is the default root ID of each of the switches. And when we want to make our root bridge, we reduce the number to 4096, so it will be the lowest among them. So let's come to our number 1, the switch number 1 here. Let's go to the interface.
Then we type the command So spanning tree.
If you look at it here now, you see our root ID is 32769 and our bridge ID also is 32769. We now want to reduce this priority here, the root ID priority here from this number to 4096. If you do that one, then it will then become our main switch or our root bridge. So let's enter the global configuration mode and then type spanning tree VLAN 1 priority. Then we enter the number 4096. Enter. That is it. We have now edited this number. So if we run this command again, so spanning tree, you will realize that this number 32769 will change to 4096. Let's give it a try. Okay. So you see here now root ID, the priority number is 4097. The same thing applies to here also. Therefore, since it has the lowest ID number, it then becomes our main switch, our main bridge, or we can call it our root bridge. Just like I told you earlier, the default root ID for any of the switches is 32769. So if you change the switch number 1 to 4096, obviously it becomes the lowest. Therefore, it is now our main switch. In spanning tree protocol, so in order to determine the path that data should follow to the destination, it is calculated in cost, whereby the lowest cost will be the path taken to forward the data. For instance, since we are using fast Ethernet, any of the links is 19. That is why you can see path cost 19 in any of the links. Each of them is 19. So for example, if you want to send data from PC3 here to PC, let's say PC1, it will calculate the cost. Let's say here is 19, here also is 19. So therefore it will be 38. If you want to take this route here also is 38. But you realize that this port number here is temporarily blocked to prevent loop. So therefore the only path right now is to pass through from switch 3 to switch 2 and then to switch 1. This is the main path being followed right now. In the event that there is a disconnection in this path, for instance, one cable cut or get disconnected, this other link will kick in automatically and then the data will continue flowing. Let me show you an example of that one, then we continue. Then I will tell you each of the ports. In doing that, let's send a continuous ping to this PC here. Okay, let's send it to this PC here, 10.0.0.1. So this command will make sure the ping command will continue sending requests unstoppable until we stop it, because we entered ping space -t, then the IP address. So as this data is flowing like this, it is following this path here from switch 3 to switch 2 and then to switch 1. But you will realize that if we disconnect any of the links, for instance, we disconnect this link here, then this link here will activate and the data will then follow this path to the destination over there. You can see right now the ping command, the data is flowing correctly, but I will now disconnect this cable here. Let's remove it. Okay. Now that I disconnect the other cable, you will realize that we will start seeing request timeout. So while it is saying request timeout, this link here is warming up. So this red button here will soon turn green, and then the data will start following this other link to the destination than the other one, because the other one is terminated. So once this one turns green now, the data will start flowing again through this direction. It will open an alternate path to forward the data to the destination. You see timeout, but once it turns green here, the ping command will start flowing normally again. Let's give it some time. Okay, you see it has turned green here. So let's see what will happen down here now. Exactly. You see now the data has started flowing again. So since this main link is being disconnected, the STP has now decided to automatically open this link now for the data to follow this path. So as we are speaking right now, the data, instead of going through switch number 2 to switch 1, it is now going through switch number 4 to switch number 1. The data could have followed this link here to switch from switch number 3 to 2 to switch number 4 and then to switch number 1. But if you check that, you realize that the cost will be higher, because this link here, the cost here is 19, here will be 19, and here also will be 19. Therefore, that's going to be around 57. But if you want to follow this path here from switch number 3 to switch number 4 and then to 1, it's just 19 plus 19, which is 38. So the 38 is the cheapest. That is why it followed this link. But if worse come to worse, if the 38 also is, this link is disconnected, our network will have no option but to take the other route. Although it's most expensive, but since it is the only one remaining, that will be the path taken. And in that case, you can see this link here is red. Right now it's blocked to prevent the data from circulating there. But once we terminate this link here, you realize that this point here, this port also will turn green. It will kick in and take over the responsibility in forwarding the packets. Let's do that one too. But once we cut the cable, we start having timeout. You see right now we are not having timeout. Just have some time. Now we cut this cable. Let's click on our we will start having timeout again. You see now it's showing timeout because this part it was following is being disconnected. So this red link here now is warming up. It will soon turn on and take over the responsibility to forward the packet to the destination. So STP always provide an alternate path to make sure the data is forwarded to prevent our network from having a single point of failure. Because if you were just having a single one line, if one cable cut, everything will stop. But now you can realize we cut two cables, we disconnect two cables, but still our data is flowing. This other point here will soon turn green and then data will continue. Okay, you see it has turned green now. So our data is flowing again. We are no longer seeing timeout. Our data is flowing again normal. Now that we have discussed the redundancy aspect of STP, now let's have a discussion about the ports, the different ports we are seeing in the diagram here. Each of these ports have different functions. The yellow ones have a different function from the blue ones, and both have different functions with the red ones as well. So these yellow ports you are seeing here, they are our designated ports. In wherever we have a link between two switches, one of the ports will assume the leadership role, whereby it will be in charge of forwarding data. So therefore, you can see the link between router 3 and 4 here. This port here, FA02, is the designated port. If you check the link between router 3 and router 4, this port here, FA02 on port number, on switch number 4 is the designated port. The same thing applies to these ones here. Although this doesn't happen randomly, there is a rule to follow. For instance, by default, any port that is on the root bridge automatically becomes a designated port. So any switch that is connected to the root switch, the port on the root switch will automatically become the designated port. That is why you can see the link between router 1 and 2 this port on switch 1 is the designated port. If you check the link between router 4 and router 1, this link on router 1 is the designated port. But now let's look at the interesting part here now. For instance, let's say the link between router 2 and router 4 here. Router 2 happens to be this port on router 2 happens to be the designated port. How is that determined? If you do our calculation, you will realize the cost between this port here to the root bridge is 19, and the cost from this port here also to the root bridge is 19, and both of them cannot be designated ports. So since their costs are the same, the next step we need to do is to check the MAC address of each of the switches. So the switch with the smallest MAC address will be the port on the switch with the smallest MAC address will then become the designated port. Now looking at the blue ports here, our blue ports are the root ports. If you check where, you realize that each of the switches here, switch 2, 3, and 4, each of them have a blue port, which is the root port. The root port is determined by the closest or cheapest to the main switch. Therefore here, in this switch here, this switch port here, FA03, is closest to this switch because it is directly connected to it. If you come to switch number 4 here, this port FA01 also is directly connected to the main switch, so it is the closest to it. And here too also, when you come to switch number 3, we have two parts here, which is this link here and this one. The same thing applies to here and here also. But in order to determine which port will be given priority, we will check the port that is connected to the neighbor with the lowest MAC address. And with the calculation with the checking we just did earlier, we realized that switch number 4 has higher MAC address than switch number 2. That is why this port here connecting to switch number 2 becomes the root port. So if the switch is not directly connected to the root bridge, it would then the port that is connected to the neighbor with the lowest MAC address would then become the root port. That is why this port here connecting to switch number 2 becomes the root port. And the red ones, which are alternate block ports, they are the ports that are temporarily blocked. They are the ports that are blocked to prevent the loops, because without that, there will be a circulation of data within the switches to the point that the network will break down. That is why each of them is temporarily blocked. But in the event that the main part had a problem, they will just automatically switch on and continue and take on the responsibility on making sure the data is flowing as it's supposed to be. This is all we have for now, and thank you very much. Let's see you in the next video.